Good morning, sir, and good morning to all participants. Welcome, sir. Thank you, sir, for accepting our invitation. So I am going to introduce about our resource person,
Thank you, Chaudhary.
Dr. Akshay Deepak. Dr. Akshay Deepak is an associate professor in the Department of Computer Science and Engineering at NIT Patna. He completed masters and PhD from Lava State University, USA in 2010 and 2013 respectively. His research interests include machine learning, algorithms, and bioinformatics. He has around 13 years of experience in academia and industry. He has been the PI of an R&D sponsored from the Science and Engineering Research Board, Government of India, and was awarded Young Faculty Research Fellowship of Visvesvaraya PhD program sponsored by Ministry of Electronics and Information Technology, MIT, Government of India. He has more than 50 publications in reputed journals and conferences. Welcome, sir. Hand it over to you, sir. Please.
Thank you, Dr. Dilip Chaudhary, sir. So it's a privilege to be delivering this talk. So initially, when I discussed with Dr. Chaube, so I was planning on doing recurrent neural networks and their applications in agricultural domain. However, Dr. Chaube and I discussed that because it's towards the end of the short-term course, and there have been quite a few theory sessions, so it would be more uh, beneficial for the participants to do some hands-on. Okay. Uh, so, so with that, I've changed the presentation goal, and instead we'll be doing hands-on. So what we'll be doing is we'll be doing classification, regression based on data sets from agricultural domain. And then, so these classification regression would be on the basis of textual or numerical data. And then we'll also be doing classification on the basis of images. Okay. So that's to give you an exposure or to a variety of machine learning tasks in agricultural domain. So hoping that all the theory that you have studied, that you have listened to so far by expert speakers, so this will sort of help in summarize and conclude the discussion, resulting in hands-on knowledge. So let me share my screen. So what I will do is first I will share this link. And in between, if you have questions, feel free to just unmute yourself and ask. I'm also joined by, so this presentation and all the tasks and the code and the demo setup have been greatly assisted by my PhD students, Anukul and Vikas. So Anukul is also part of this presentation. So what I've shared with you a Google Drive folder. If you go into the folder, so there are three folders: crop type recommendation, plant disease classification, and soil moisture prediction. I hope by now all of you are comfortable with running code in Google Colab. If not, let me know. I hope Dr. Chaube sir told me that he has done one demo, one practice session. So if you go, there will be 3 folders: crop type recommendation, plant disease classification, and soil moisture prediction. If you click on the link that has been shared with you, that is, we click on this link. Yeah. If you go on this link, you'll see 3 folders are there. So because we'll do image classification at a later stage, but because the downloading the data set is going to take some time, what I would recommend is put, so there are 2 data sets, plantdisease.zip and plantdisease.small.zip. Okay. So actually this plantdisease.zip is also a smaller version of the original data set, which was, I believe, around 1 gigabyte. Is it reduced for fast execution? Even further, I've reduced it even further to plantdisease.small.zip. So if you have reasonable broadband, reasonable speed broadband, you can download the larger file, plant disease. Otherwise, just download the plant disease small.zip file. Okay, you can download it from here. And once, so you can put to download. So downloading will take some time. Okay. Let's say we do, if we do plant disease small, okay. If we do plant disease small, there is a folder called dataset small. Now we need to update this data, upload this data set into a collab. So the way to do would be, let's say I create a new folder, live practice, disease classification. Okay. So there, once I have downloaded this plant disease small data set and extracted it, I'll see, if we go into that folder, we'll see there is a folder dataset small. Okay. Just select this folder and drag and drop it to your Google Drive folder. It will take some time. It will take some time. It starts with, it says 19 minutes, but it won't take that much. I think it will be done in 5 minutes. Okay. If you have, as I said, if you have really good broadband or high-speed internet, you can download the larger data set. Larger data set also has same data set folder. Previously, data set folder was data small. Now the data set folder is simply data set. Again, you have to do the same thing, drag and drop here. If you drag and drop the large data set folder, it is going to take some, maybe around 20-25 minutes. So it's all right. So whatever you do, just download it and put it for upload. Okay, and leave it. We'll come back to this later. Meanwhile, we'll do regression problem. That will take half an hour. And then we will come back to this later, hoping that the upload will be complete and we'll be able to run our code. So I hope all of you would have you would have downloaded this and put this to upload. I hope the instructions are clear. You have to go to plant disease classification folder. Here there are 2 zip files, plantdisease.zip and plantdisease.small.zip. So this one is 700 MB around. This is 152 MB. Whichever you want to download, depending upon your speed of broadband. The problem with the small data set is that because the samples are less, the training and testing won't happen as well as it will happen in larger data set. So that will give you, you won't be able to see convergence in coming into picture. We won't be able to see convergence coming into picture. So that's why plant disease.zip larger data set would be better. However, if not, I can simply download the small data set, and later when you have time, you can repeat the experiments with the larger data set. Okay. So now once we have done that, then what we'll do is we'll go to soil moisture prediction. This is the first task where the goal is to predict soil moisture. So go to this folder and right click and download the two files as shown below. I hope my screen that I'm sharing is visible to everyone, and people are able to follow. A yes from someone. A yes from someone would be appreciable. Okay. Okay, great. So I get a thumbs up. People are able to do it. So download this soil moisture as well as download this Python notebook. Right click on download. Okay. Right click and download. So once you download this, in your downloads folder, these two files will appear: soil moisture and soil dot this CSV file and Python notebook. Again, what you have to do is, in this live practice session, I will create a folder. I'll create a folder here, new folder, live practice, for soil moisture. I have created this, and I'm going to drag and drop the code and the CSV data set to this. So this happens quickly, and by now we can see that data set download is also ready. Okay. The data set has been uploaded successfully because I used a small data set. It has been uploaded successfully. However, we'll continue with the regression problem of soil moisture prediction. We'll continue with the regression problem of soil moisture prediction, so that in case if somebody is, if the data set uploading is taking longer time, it's all right, we will wait. Or if somebody has opted for downloading the larger data set and then uploading the same, they will also get some time. Okay. So I hope by now all of us have uploaded the Python notebook and the soil moisture data set. Now let us click on the soil moisture data set. Okay. It will open with this. So we see the soil moisture data set has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. So out of this, the F column is actually the class label, the soil moisture that has to be predicted. This is a regression problem. First, we'll predict soil. Then we'll see what is the recommendation our machine learning will give for the crop that we need to grow up. And then once we have planted the crops and the plant is up and growing, and then it's susceptible to diseases. So then we'll do a machine learning analysis on disease prediction using plant leaves, images of leaves of plants. Okay. So first is soil moisture prediction. So here we see this column SM gives the soil moisture value. Okay. So this is what we need to predict. This is the output that needs to be predicted. Apart from that, we have time and PM, these two other values, soil values that have been captured. So 1, 2, 3, 4. AM is irrelevant or useless value because it's all zeros. We will drop it eventually in the code. So we won't count this as a feature. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 feature values. 1 is a useless feature, that is a 9th feature, and 10th is the output class. So that's the overview. Okay, that's the overview of the data set that we're going to deal with. Okay, we go back, and now we click on this code. See, you have to download the code and then upload it in your own Google Colab directory. If you try to work on the file that I have shared, the file has been shared in read-only mode. You won't be able to modify it or run it, okay, because it's shared in only read-only mode. Because everybody starts modifying it, then I won't be able to run the code. Okay, so you have to download it and then upload it in your Google Colab, Google Drive folder. Okay. So I hope all of us have created a folder, whatever folder you want to name it. I have named it as live practice on soil moisture. And this is my code that I'm going to run. Okay. So this is where we have gotten our data set from in the third cell block. So we can just copy and paste in browser to see what is the data set where we have gotten this data set from Kaggle soil moisture prediction data set. Okay, small data set, different columns are there, and codes, and also we'll get all these things. Okay. Output and logs, and so this is where we got this data set from. You're curious, you can also go yourself and download it. Okay, so let's first do the run the code. I hope all of us have uploaded it and are good to run the code, right? Great. So let us run the first. So it's just mounting the Google Drive. So it's connecting to the Google Colab runtime. So it's now ready. So it says Google 3, connect to Google Drive. I'm giving it permission. Okay. Continue. So this happens just once. Continue. Okay. So it's taking a bit of time. So now it took 37 seconds. So first time it takes longer than expected. It takes longer time. So now it has been mounted in this, and we see that this runtime system is also connected. Then we import some standard libraries. So what we'll do is we'll run this code together, and we'll try to understand what is happening in code. And later, what is expected of you, or what is suggested to all the participants, is play around with the code. That is, modify small things here and there, try some other data set, or drop features, drop columns from the data set, change some regression output values to be predicted, and so on. Now, what we do is we read the data set. So this data set is actually here. So intentionally, I've moved it to some other folder. So I need to correctly specify the folder from where it is there. So what we do is we click on this icon. We see my drive and navigate to where we have uploaded the folder. Okay, NIT. So live practice soil moisture prediction, and I click on this and I do copy path. I do copy path. And the same path has to be copied here. So we see this is my path and live soil moisture. So I will copy this and paste it here. Right. So this is how we update. We navigate by clicking on the left files icon. We navigate to the folder where we want to go. And then wherever this CSV file is placed, there we go and copy the path. Yes, we do. Click on these three dots copy path, and we do it. Right? Okay. So now, so we read that CSV file, and then we are printing it. So if you are able to see something like this, it means we have mapped to the folder successfully. That is, we have specified the file path successfully. If anybody has problems, feel free to raise your hand or unmute yourself. Okay. So now we are able to do this. We see the same 10 columns appear here. So our mapping has been done successfully. If you want, you can click on these recommended plots. It will give you frequency histograms of all the different columns and the distributions and so on, and the pairwise distributions. You can try it out. Then what we do is we print head 5, the top 5 rows. Okay. And we print the tail, the last 5 rows, the first 5 rows and the last 5 rows. By running this, we get the last 5 rows. And then we print the target column. So this is a value that has to be predicted. Okay, this is a value that has to be predicted. Okay, this is a value that has to be predicted. Okay, so we see this is real value soil moisture prediction, just to see. And then this is df.describe. So describe actually prints statistics about the whole data, different features like mean, standard deviation, minimum, and so on. Okay. In the 25%, what is the max and so on. So this denotes, I believe, distribution of data at 25%, how much it is covered. If we go from 0.55 range, how many 25% of data is covered till what value, and so on. Max is 6.7, mean is 1.5. So if you go till 1.1, include all the values till 1.1, 50% of the data is covered. So it gives a distribution of data. Right? And then this is important. We click on this to print the shape of the data. So we have 20,166 samples and 10 rows. The same thing, data.info prints the data summary. What is the type of the data? All are float values, real numbers. Okay. Time is an object. It's a float real numbers. Time is also a string represented as an object. And then this gives the data types of each column. And then this gives the unique values for each column. Okay. So we see time is of course unique for each column. If we see total number is 20,166, so each has a unique timestamp. So time has 20,166 unique values. Others don't have those many unique values, which is expected. Then we count the number of not empty values for each, because we don't want empty values. We have to deal with empty values. There are ways to deal with empty values. Fortunately, for all the features, there are no empty or missing values. Had there been missing values, there are ways to deal with average, or we put 0, or we drop those rows, or whatever. We put -1, something like that. But here we don't have any missing values. Then what do we do is the same thing can be confirmed by this: is there is any empty value. So all false denotes no empty value, true denotes empty value. And this also counts, the same thing, it counts. There are no empty values. Okay, here we will counting not empty values, and here we are counting empty values. So from both the ways, we get the empty values are null. Then here what we do is we are dropping the column AM. If you remember, there was a column here, AM, which is useless feature. It's all zeros, so it's not going to be any useful in the regression task. So we drop that. Okay. We drop it from our data set. And again, we check if it has been dropped. Then we check the number of rows and columns again. So we see the number of rows is the same, but the number of columns has reduced by 1. So it is 9. Then we are just plotting this frequency histogram, okay, of SM, our output class label. So this is the histogram of how many samples are there for different values, soil moisture prediction. So on the x-axis we have the values that need to be predicted, and on y we have the number of samples. And then we can do further analysis, do a correlation. So it's all just analyzing the data before we go to the actual part. So correlation values, this is helpful, and this because if you want to drop features, because we know that if two features are highly correlated, then one feature is going to be enough for the regression or the classification task that you're going to do, because both features are pretty much going to convey the same information. Okay, so we do data, so we see, and the same we can visualize the heat map of correlation. So when we visualize the heat map, we see, of course, the column values are all 100 because each feature is 100% correlated to itself. And then the lighter the color, the higher is the correlation. Okay, so sometimes the correlation is 93%. So PM3 has a very high correlation with PM2. So in this code, we haven't dropped any feature. But as I said, when we go back to your hostels or wherever you're living, we can go back and try dropping certain features from this data set and see if the accuracy improves. Okay? Having a lot of correlated features, highly correlated features is not a good thing. So at times reducing the dimension can help. We can also explore different dimension reduction techniques. That is something that's left as an assignment when you go back. So this correlation matrix. And then we are just converting the data into a format that is required, dividing the data x and y, required for NumPy. So again, we print the shape. You see that it's the same. This is the target, and this is my trained data. Okay. The trained data, we are splitting the training and testing. Sorry, not the training and splitting. We are splitting the data into x and y, where x is the features and y is the label. Okay, so this is label or value to be regressed, and these are the features. These are 7 features. One feature has already been dropped. So actually 8 features. 0, 2, 7, 7 is one feature has already been dropped, and 8 is the value to be. So we are taking only 7 features. I think. Okay, sorry, we are not taking the time. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6. Yeah, 3, 3, 6, and 7. So we are only taking 7. We are not taking the time, the 0th column. So we are dropping the time also because timestamp. It's not going to be useful. It's just timestamp. So we are not taking the time value. So we are excluding the AM. We already dropped the AM. We are excluding the time stamp, okay, which is indexed at 0. And the 4th is the actual output regressed value, class value. Okay, so we are excluding the timestamp. So we are taking 1, 2, 3, 4, 5, 6, 7 feature values. So 7 feature values, including the timestamp, and so this is the output label, and these are the features. And just print them, the features, to get an idea, okay, whether things are going right or not, and we can print the labels also. Okay. And then we do splitting of data set into training and testing. Okay, so we are doing 80% training and 20% testing. So this fair standard API for train test split. Random state decides, the value of random state decides what randomization we are going to do while fetching the data from training and testing. So data is not fetched in this. It's not that the first 80% of the samples will be considered for training and the next 20% for testing. There's randomization in there. So we can put any value here. Usually we fix a value so that because of first time when we run our code, rarely returns, it rarely runs perfectly. There's always be some errors and bugs to be fixed. So we fix a random state value to ensure that the set of training and testing, subset of training and testing is the same. It is randomized, but same. Once we are done, we have fixed our code, everything, then we can feed this truly random value like a time, system time or something, so that in every run, the train and data set generated for train and test rate is totally different. Okay, then we normalize the values. We normalize the value. Normalization means putting the values between -1 and +1 with 0 as mean and unit standard deviation. This is an API for doing that. And if you see, the values have now been scaled between -1 and I think it's unit deviation and 0 mean, not between -1 and +1. The thing is, should be 0 mean and unit standard deviation. This is the standard normalization process. So we see all the values are now between 0 with 0 mean. Why we do 0 mean is because it's easier for the model to learn. Okay, it's just that if I'm a teacher and if I'm evaluating students, okay, so let's say one college has grading between 0 to 100, where the maximum marks are 100, and another college has grading between 0 to 300. So obviously, it will be easier for my brain to evaluate or to select students if all of them have marks between 0 to 100. That is, the maximum marks is 100, rather than otherwise I have to mentally adjust to compare a student who has got 95 out of 100 with a student who has got 280 out of 300. Okay. So same thing applies for machine learning algorithms also. So that's why we normalize, put the data in the same range, the same mean. Okay. Right. And so the same thing we do for testing. We see this is X train and X test. That is the features, train set of feature and the test set of features. And then the Y train and Y test, the label set of the training and the testing. And then we do regression. So regression problem is, I hope by now you would be familiar with what is regression. Regression is predicting value where the output can be a real value. Classification problem is output can be one of a given number of classes, fixed integral values, but in regression they can be real values. So we do linear regression. We are using linear regression. We'll see 3 regression models. So we instantiate that and we do fit. So fit is a function which is called for any machine learning model, training and testing. So this is linear regression. It tries to fit the training data. And then once training is done, we predict it on the test data. Okay, and these are the prediction result. We do printing. So this is a prediction result. We simply type it. It prints the prediction 1 array. So it prints the prediction result. And then it prints the R squared error. Okay, so you look up what is R squared error. Generally, it captures the variation, the correlation with the output variable of the input. So the higher the R value is, the better the results are. Okay, the higher the R value is, it's a value between 0 and 1. So higher the R value is, the better the results are. Okay, so we get an R value of 0.7. There are also other metrics, mean squared error and so on, which you can explore. And that's what I mean by playing around with the code. Look at other metrics that are used for regression and print them. So we get R squared error, which is 0.7. And so this is a value for when we do regression using a linear regression model. And then we can do the same using XGBoost regression model. So again, you see the code for XGBoost and linear regression is pretty much the same. We instantiate and we call fit. So there's a model. And then once the training is done, we do prediction. Okay. We do prediction. And then we again compute the R squared score. We see we have a higher R squared score of 0.98 as compared to linear regression. So this XGBoost regression is definitely doing better than uh, linear regression. And then, okay, yeah. So this is a regression score. And then the third regression we're going to try is decision tree regression. So decision trees can also be used as regression models. So we do that. So again, instantiate same code. We import the library, we instantiate it, we call. This is third regression. And then we train, and then we do testing, we do prediction. Okay, and these are results we get, and we print the results. We pass this from this prediction result, and we see. So this gives. This also gives a high value of 0.96, but the best value was obtained using uh, XGBoost regression, which is 0.98. The second best was 0.96, and the third best was 0.7. Now we can plot this. We can plot this graph. Okay, we can plot this using graph. The comparative model between these three, we can plot using graph, which is left as an exercise. I think in the second assignment, we are also plotting graph. So you can take the graph code from there and update it. Otherwise, you can take it as assignment. Okay, so any questions so far? Any questions so far? How many of you were able to do it? Follow it step by step. So code was given, you just had to run it. Can I hear done from participants in the chat box? Okay, so there was no coding as such. Great. Great. So at least 2 participants have done it. So it's very encouraging for me personally to see some of you are able to do it. Okay. For others, we'll wait for a couple of minutes. You don't have to, just all the code is given. If once you fix the path to the directory, then the rest of the code simply needs to be run. Okay. The rest of the code simply needs to be run. Okay. I believe that quite a few participants are offline at IIIT Bhagalpur, and those who are offline in the sense, I mean, who are present physically and attending from Bhagalpur, IIIT Bhagalpur, you can take help of others who have done it. So this is what usually helps. Yeah, I would have liked to be there in person. And this is what Dr. Chaube and I had planned. But anyway, so great. Excellent. So I've got 5 dones so far by the students, which is great. Very encouraging for me. Thank you for participating. So with that, I'll move on to the next assignment. In between, we'll just check if our upload of the dataset has been complete. I believe it has been around half an hour to 40 minutes. So we'll come to image classification problem now. Okay. So live plant disease classification. So you see the data set. This is data set small. Okay. This is the data set small. This is a data set small they have done. Okay. So if you click on the dataset small folder, you will see there is test, train, and validation. So the original dataset has, I think, a lot more images in train, test, and validation. So we have reduced it so that we are able to upload it runtime, and we are also able to upload it in a reasonable amount of time and also run the code for sufficient number of epochs. If you see test folder, you'll see there are 3 categories of this data set. So this. Let me just open this Python image classification. So the folder that has been shared with you, if you go to the plant disease classification, you will see image classification Python notebook. Right click, download this file. Once you have downloaded this file, then go to the folder where you are working currently, where you have uploaded the data set. Okay, there again, select this file and drag and drop it like this. So once you have dragged and dropped, you will see this file. Click on this file. Okay. Click on this file. Okay. Right. Click on this file. We'll see that the same. We'll see. Go down this. Okay. So before, if you click on this file, you will see this is the date source of the data set. This is the source of the data set. So this is. So the data set contains 3 labels. These are data sets of images of plant leaves. The data consists of 3 labels: healthy leaves, powdery leaves, and rusted leaves, referring to the 3 plant condition. So given an image of plant leaf, we need to predict the class it belongs to. So there are a total of 1530 images divided into train, test, and validation sets. I've made it really small, so it's like total maybe 180 images in total. So less than 10%, around 10% of the original size. Original size is around 1 GB. So so it's really reduced. The small data set that we are using is really small, so that we can run it during our experimentation. So let's take at some of the images. So if you see on small, click on it, or I think we can just look at here. Yeah. So this is a test data set, train data set, and validation data set. Okay. The test data set, if you see healthy, how does a healthy image look like? This is what a healthy leaf image looks like. And there are other images of leaves. And then if we see powdery, image of a powdery leaf, this is what a powdery image looks like. Yeah, so it's diseased. And if we go to the rusted set of leaves, this is what the data set looks like. Rusted leaves. So we need to classify into one of the 3 categories. Great. So I hope all of you are successful in uploading either the large data set plant disease.zip or the small data set, at least one of them. Okay. So with that, we'll move. So in this data set, so here is a small data set that these 3 subfolders appear. So can I get yes from participants, those who have uploaded this data sets and are good to code along with me? Uploading done. Great. 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 Okay. So any others? Yes from others? At least a yes from 3 more participants would be very encouraging for me personally. Okay, great. 2. Couple of more yeses. Come on. The data set is small, right? The data set is small. Any more? Someone else who has uploaded the data set successfully to his Google Drive folder. Okay. Just in case if you missed it, based on the link that has been shared with you, go to this plant disease classification folder. Right click on this dataset small, plant disease small.zip. Right click on it, download. Once you have downloaded plant disease small, okay, so this is a zip file. Right click, 7-zip, extract to plant disease small. Extract all the files. Okay, so you'll see there's dataset, dataset or dataset small, whatever you want to keep. So yeah, so this is dataset. If you just select on this, let me just delete this folder and extract it again. Okay, so there's a folder dataset. If I right click properties, we see there are 180 files. Okay, so I can rename it here, dataset small. Okay, and then I have to simply drag and drop it like this. So because I've already uploaded it, it will say give these two options. I will cancel it. I don't want to repeat the process. This is what we have been doing here. Okay. Okay. So this is what we need to do. So once we have done this, okay. So go to the folder where we have done this. So now we have this dataset small folder and this. Let us open this image classification notebook. Okay. So we first run this code. So it's already connecting it. So we have to again fix the file. So let us connect it, because without connecting it, all the folders will not be shown here on the left side. Okay, it's mounted. So now you see the drive folder appears. So my drive. Then I go to navigate to the folder where I have actually stored this. Yeah. So this is the folder dataset small. Okay, and click on these 3 dots and copy path. So this is going to be dataset small. This entire thing is going to be pasted here. So run this. Then this is just a function that returns the number of files present in a folder. This is the utility function that we have coded, because we need to count the number of sample image files in each folder. So let us just run this. And now we fix it. So you see the code previous output is 200, 200, 200, because the first time that we ran this code, so this was on the larger data set that has been uploaded. So it has 200 samples of healthy leaves and powdered leaves and rusty leaves. But now if we run it, the number of samples would be quite less. So it's 30, 30, 30. Okay, because we have reduced the number of samples drastically so that the upload is fast. We can do upload while we are doing during this session only, and we don't have to spend like 1 hour, or just have to wait for a couple of hours to upload the data in the Google Drive folder itself. So if you are getting this message, it means you have uploaded the small data set correctly. Uploaded the small data set correctly. So how many of us have gotten this message? Number of healthy leaves is 30, 30, 30. Data set, plant disease data set loaded. Okay. Okay. Can I get a yes from whoever has done it? Okay, great. So somebody has done for larger data set. Excellent. Excellent. Great. So that's very encouraging for me. Thank you. Okay. So we do this, and then okay. So this is the number of files in each data set, and the same thing we do for validation data set files. Okay. So this is a training data set. Okay, because we have to correct the path here. So that is why we're getting this error. There's something nice that happens when we're doing practice, when we're running the code runtime. We get to see fix errors. Though I cannot guarantee I'll be able to fix all the errors right now. So that's why I have my PhD students along with me, because they are the ones who do a lot of experiments to help us. Okay, so now we do this. We see in validation set also there's 15 images in each category. In the training set there is 30. In the validation set there is 15, and again in the test set. Okay. Let us run. Okay, so test is also 15, training is 30, test is validation is 15, and test is 50. So I hope all of you know what is training data set, testing data set, and validation data set. Okay, training data set is on which a model trains. It's like the practice questions that you get when you're attending a course in your college throughout the semester, the questions that your instructor solves on board, and the questions that gives as a practice assignment. Okay. Testing is the set of questions that you get during your end semester exams. Okay. Validation is the test series that you join. Okay. There's a different set of questions than what you have solved, but to evaluate how well you are doing, you are learning the class outcome, you take test series, which is different from your final end semester exam, as well as this set of questions that are solved during in class. The purpose of validation is to detect overfitting so that your model is not generalizing too much and paying too much attention to the questions that are being taught in class, and not looking at other variety of questions. Okay. So it's overfitting. Okay, so we have validation, train, and testing. And then let's denote a sample image again here. We'll do correct this and correct this and correct this. Okay, so we are displaying a sample image from my healthy data set, healthy leaf, a sample healthy leaf, and a sample okay. Right. No, because this I've deleted this image. Okay. So what we'll do is, because this image was actually taken from when the data set was large, 200. So what we'll do is, this is test and yeah, data set test and Rust. rename, Control C, and Control V, and run it. Yeah, this is example of rusted image. So why we were getting error is because originally I ran this code on that 200 image data set, the larger data set. So some of you who have used a larger data set, you won't get this error. But to reduce, to make the data set even really small, I deleted almost like 70% of the images. Okay. Now run this one. Maybe here also we will get error. Yeah. So this is train boundary. Train It's taking longer than expected. So bear with me. Okay. So this is boundary. Okay. Okay. Now, so we have. I hope all of us are together, or a lot of us are together, or at least some of us are together. The rest can try this when you go back to your respective places. So now what we do is, now we have loaded the data, we have done training, test splitting, and everything. Now we are going to do training. So for training, the usual practice is we don't take the training data as it is, but we slightly modify the data. That is, we introduce noise in the data. The idea is because the training, the images are likely to look similar, training and testing images. So if we introduce some noise, some slight variation in the training data, then it will be more challenging for a model to learn. So if a model can learn in challenging conditions for challenging data set, then obviously it will perform better in real life. So for that, what we do is just only the training data set. Okay, only the training data set. We use what is called image data generator. So we change the image slightly. There's a shearing operation, there's a zooming operation, and there is a horizontal flip that is being done through. So we are training, we are changing the data. So whatever is the data, okay, train data, whatever is the data. So we are saying that we are classifying we are classifying we are instantiating an image data generator where we are giving it parameter. We haven't generated images yet. We are just instantiating two for training and testing. Now this first parameter actually just normalizes all the values, the pixel values between between 1 to 255, 0 to 255, 1 to 255. Okay, rescales the value so that all pixel values are between 1 to I think 0 to 255. I'll have to look it up. But the purpose of 255 is that because generally the pixel values are between between 0 to 255, but just ensures that it is like that. Okay, it is rescaling it. The pixel values are between 1 and 255. It is rescaling, dividing it so that now the values are between 0 and 1. I'm sorry. Yeah, this is a rescale parameter because the pixel values originally are between 0 to 255. So it is dividing it by 1 by 255 so that now the values lie between 0 and 1. Then what do we do? we apply this data augmentation technique on this data set. Not here, copy the path from here. Actually, we should have done specify this as a as a common string, and then we could have appended that string everywhere so that we won't have to do copy and paste. So we are instantiating and initializing image generator, and then from here we are fetching the images. Okay, the target size is 255 by 255. It's also resizing the images into 255 size 256. The original size is quite large. Now, the larger the size is, the more parameters we need, and so on, and the more parameters and time we need for training. Okay, so here the batch size is 32, but however we just have 30 images. So I think the batch size can be, let's say, we can keep the batch size as 10. If you're using 200, keep the batch size as 32. Okay. Or just we can keep the batch size as 8. I hope it won't land me into trouble later. Target size. Okay. Okay. Yeah. Okay. The same thing we do for the validation images, the test images. Now you see, again, we have to fix the data set path. It's good to get some errors so that we know whether we are really learning or not. To see one thing, for training data set, we introduced noise. Okay, but for testing data set, we just did rescaling of the pixel values. We did not introduce any noise. Right? There shouldn't be any. This should be very obvious, because testing data set we cannot interfere. We cannot play around with the testing data set. It should be as it is. Okay? Testing questions are testing questions. For training, we can introduce noise. So that's why you introduce noise in training data set and not in testing data set. Okay? And then we do this. And then what we do is we apply a simple convolution neural network model. Okay? So I hope somebody would have covered convolution neural networks by now. If not, it's a very proper neural network. It is a very popular neural network model used for analyzing images. Okay. So this is the structure. The first is the 2D layer having 32 number of filters, and the number of filters is 32. Size of each filter is 3 × 3. The input shape is this 225. Activation function is ReLU. Then there is max pooling layer. Then again there is a 2D convolution layer. Again max pooling. So there are 2 convolution layers followed by a flattened layer. There's a dense layer. And then there's a final output layer having softmax function. So softmax function we use at the last layer because it is a multi-class classification problem. There are more than one classes. And before that, we always use ReLU, because ReLU function introduces non-linearity and it has a high slope value. So the error gradients are propagated better. So let us just create this model. So we're just creating this model. Okay. And now we are compiling this model with this loss function and accuracy matrix and optimizer as Adam. We can look all this up. Okay, there are different other optimizers also and other loss functions also. This is what is typically used, but you should have an idea of what other values are. And here we print the model summary to see what is the model. So this gives all the layers of the model. The first 2D layer, max pooling layer, another 2D convolution 2D layer, then the flattening, and the 2 dense layers. There's a total number of parameters. So this is the total number of parameters is what defines the complexity of the model. You see, the pooling layers don't contribute to the trainable parameters, because pooling operation does not involve any trainable parameters. Okay, done. Now, here we'll do batch size as 4, because previously the batch size was 32, and during fitting we are doing half of that. It means among those batches we are splitting it further into batches of 4. So if you're using that 200 data set where you have 200 samples, you can let the batch size be 16. Otherwise, you can change it. Okay? And the number of epochs for which we're going to train is 4. Size for validation batch size is also 4. Let us train it. I hope the training should happen yeah, reasonably fast. Okay. You see the batch size is 4. So 4 is, I think 12, 4 is this. So batch size was 8 here previously, and the number of images were 30, 30, 30, 90. So 12 8s is 96. You see the batch size that when we were generating the image here, here the batch size, we have given the batch size as 8. Okay, and there are 30 images for each of the 3 categories: powdery, healthy, and rusted. So total there are 90 images. So batch size is 8. So there will be 12 batches. So that's why we see in each box there are 12 batches. Okay. Okay. While this runs, first thing we'll do is we'll wait for a couple of minutes. We will wait for a couple of minutes so that the rest of the participants of this short-term course are able to reach this point. Still, if it's going to take longer time, we are going to move to a third assignment, which is classification problem. Okay, so this sort of image classification was sort of interleaved in between, because first the upload was going to take time, and then this image training is always a time-consuming operation. So this is going to take time. So that's why we'll, instead of simply waiting here for the result to complete, we will move on to the next task, which is classification task, which is actually which we plan to do, the second task. The first was soil moisture prediction, where we decided what is the moisture of the soil, and then once we have predicted that, then we used we're going to decide which crop are we going to plant, are going to cultivate, which is the crop recommendation classification model that we're going to discuss. And once we have done this, when the crops have grown, then we do disease classification. We take images of plant leaves through drones or whatever, and then we feed it to a model, which we're doing right now. So how many of you have reached this stage? How many of you have started running the model, image classification model? Anyone? Anyone who has started running the training process for the plant disease image classification task? Anyone who has started running the training process for the plant disease image classification task? If you're having problems, just type or unmute yourself or let me know. Okay, great. Anyone else? Okay. I hope there's really nothing. There's nothing complex. Just have to run the code. You have to run all the code. Okay, so those who are doing on the working the larger data set, it may take up to I think 30 minutes to 45 minutes, the training, or maybe 30 minutes. So in that case, you can just let it be and run. One more yes would be super encouraging for me. One more yes, if anybody has done it. Yes. Anyone else who has started the training? Anyone else? Okay. Okay. If not, you can, you can try training at your. Okay. So now we will move on to yeah, the third assignment. The third assignment. Don't close this browser. Okay. Don't close this browser. This window. Let it run. It will take time. Okay. Let it run. We'll go to third assignment. The third assignment is crop type recommendation. So let me create a folder, live practice crop type. Okay. So what we go, before you see there's a crop type recommendation folder, go to that, right click on the data set, download, right click on this Python notebook, download. Okay. Then go to, so this is, you will get from where you have created the link that has been shared to you. Okay, because for me the link and the folder are from the same account. That's why I'm able to shift so quickly. Then go to the working folder where you are doing assignment along with everyone else. So that will be this folder. I go to my downloads folder. Okay, so I copy this and the CSV file that I've downloaded, select it, drag and drop it to the Google Drive folder. Okay. It's uploaded. Okay, it's uploaded. Right. So now it's uploaded. So now what we do is, we open the Python notebook. By the way, that is still running. Let it run. You're running for 20 epochs. If you're really, because it's running on cloud, so for all of us to take the same amount of time. But if you're really short on time, you can cut the number of epochs to 10 or even 5, whatever works for you. Okay. Now, if you see the crop data set, this is a link to the data set. Yeah. So I think it has 8 columns. Okay, the features. 1, 2, 8 columns it has. 1, 2, yeah, 3, 4, 5, 6, 8 column, and the output it has is the number of crops is how many crops are there, Anukul?
22.
22 crops are there. Okay, the number of crops is 22. So what we can do is the source of the data. If you look at this, open this. This is a label. Okay, this is the crop label. Let us just open in an Excel. Yeah. It's 1, 2, 3, 4, 5, 6, 7. So 7 are feature values and the recommended crop. The data filter. So you see there are 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay. If you want to see the number of unique values, we can simply paste it and then remove duplicates. So 23 unique values remain. So there are 23 different fruits that have to be printed. 22 different values remain. So 22 different, excluding the blank, there are 22 different crops that are to be predicted. So these values are chickpea, kidney beans, pigeon beans, moth beans, mung bear, black gram, lentil, and so on. Okay, so this is the data. So this is what the data looks like. We have to, I think this is the level of nitrogen, potassium, sodium, temperature, humidity, pH value, rainfall. And based on this, we have to recommend the crop that should be planted. I hope the task is clear to all of us. Okay. Right. So now, okay. So let's open this. Okay, we already opened this. That's it. Okay, so we have already opened this. So let us run this one by one. So I think we can create too many sessions. इमेज वाला ना, तो इमेज के साथ तो पहले भी चल रहा है. मैनेज सेशंस. ओके, सॉइल को बंद कर देते हैं ना. Even though I hope it does not delete the soil code. It shouldn't. But let me just check. Okay, great. It's there. Yeah. Live. Yeah. Okay. So if we open this, now we should be able to run this. Yeah. So it does not allow more than 3 sessions at one time. Perhaps you did not get that error. You may not have gotten that error. It's all right because I have 3 sessions open. You may have just got 2 sessions open. It's all right. Okay. So now this mounting is done. And then we import the libraries. And then again, we have to specify this path. So go to drive, my stuff in Google Drive. Live practice crop type. Copy path. Run it. Let's hit it. Yes, and we are happy because we are able to load the CSV file successfully. So we are good to go. Okay, we can see all the file, the labels, the 8 columns, 1, 2, 3, 4, 5, 6, 7, 7 columns, and the label has been loaded successfully. If you want, you can click on this and try the recommended plot. Let's print the data set summary. Okay, the different column headings, the data types. Check if there is null value. No, there are no null values. Excellent, we are good to go. Just describe the data statistics, mean, standard deviation, and so on. Print the columns. Okay, these are the columns. These are the columns. Print the unique labels. So these are 22 fruits, rice, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22. Okay, print the shape of the data. Label encoder, we need to encode the labels because computer understands only numbers. So we convert these string values to numbers. There are 22 different fruits, there are 22 different labels. Okay, now you see if you print the data, you'll see instead of the string values, now we have labels as numbers. Okay. Okay. Then we convert them to list and then to unique labels, so that we get something like this: apple is 0, banana is 1, black gram is 2, chickpeas is this, and watermelon, the last crop, is 21. Okay, then because we're going to try 3 different models, we are just storing the models in uh, a list. Okay. So all the accuracies would be stored in this list value, ACC and models would be stored in model list. So we click on it. And then we are dropping the label from features. Okay, the label, the final output label, that shouldn't be part of the features. This is standard practice. Every time we do this, we drop it from the feature set. And then we do a split into train, test, and split. We see the ratio is 90% is for training and 10% is for testing. Here we use a different random state value of 42. Okay, and then we normalize the data. Normalization means with 0, 1, with 0 mean and unit variance. Okay, and we again we do the splitting of the data. I think yeah, this could have been done later. Okay, okay, is it? But they're doing on the same X, Y, and train. So we can do, I think we can do normalization before in one go, right? Okay, so never mind. I think if you have just done this after splitting or after, yeah, it wouldn't have made a difference. Okay, so this train, okay, here we are doing splitting again. Here we are doing normalization, and then we are doing train test it. So this is work. So this operation turns out to be written here. Okay, so that's done. And then what we do is the first classifier that we're going to apply is random forest classifier. So we fit the model into train and Y train and X train, and then we do prediction, and we get the score of the model. So all the things we are doing in one go only in this code block, because so far there's a third data set that we are working on. So we are doing all of this together. Okay, so we get the accuracy as 1, 1. So it's like the accuracy is quite high, 100%. Okay, on the test as well as on the training. Okay, now let's print the confusion matrix. All this is for random forest data set. So we see confusion matrix is excellent. There is no confusion apart from the diagonal. There's only diagonal values. Non-diagonal values are 0. So there is no confusion. This model is absolutely clear what it wants to do. There's no confusion. There are no non-diagonal. There are no non-zero non-diagonal values. Okay, these are the different metrics: weighted and micro, and weighted and non-weighted values, and accuracy values, precision recall, and F1 score. So I hope by now all of you know what is precision recall and F1 score. Then the next classifier we are going to use is decision tree. So that is what we did for random forest. The same data set we're going to use for decision tree. In decision tree, we see the accuracy is slightly reduced, very, very, very infinitesimal difference. Okay, the training accuracy is 100%, the testing accuracy is 99.09. Good to have some variation. So again, we do print the confusion matrix for the decision tree. And then we print the confusion matrix. We see there will be some confusion. Let us try to spot the confusion. This is the confusion, and this is the confusion. So these are non-zero values. This can be a good example for puzzle also. Okay, where we are given the task, the odd one out. So we see all non-diagonal values are 0 except this and this. Okay, that's why there is this slightly 99 point score is 99.09%. Okay, great. So with that, we move on to the last third classifier, which is K nearest neighbors classifier. Now, if we run that, we see the accuracy is even less, slightly less, but still very high accuracy. So it's 98.9% for on training set and 97.7% on test set. Okay. See, again, we plot the confusion matrix. So we'll see somewhat more non-zero values, non-zero, non-diagonal values. Right? There is 1 here, there is 3 here. Maybe in the upper half of the diagonal, there's no confusion. But the lower half of the diagonal, there are 2 values. So this is the weighted and non-weighted accuracy matrix. And then we finally do plot a small graph to compare the accuracy. So we see the random forest gives the highest accuracy, then next is decision trees, and the KNN is even lesser accuracy. But all 3 produce fairly accurate, almost close to 100% accuracy values. Then what we do is, because random model turns out to be the best, so we are using that in real life. So this is how to use trained models. So let's say you hired 3 machine learning engineers. One proposed a random forest, another proposed a decision tree, and the third proposed K nearest neighbors as the model, and they all gave you 3 different results. And then as the main person or as the head of the institute, you finally decide to use random forest as a model. So now a farmer comes to you, or assisted by some technical person. Okay, for this farmland, these are the feature values that I get. Now tell me, what is a crop that I should plant? So you have already trained that random forest model. So you predict the value, and you get the recommended crop is coffee. You recommend the coffee crop to be planted. So I hope some of us were able to do this. Okay. See, there's really nothing, don't have to type apart from changing the path. There's really don't have to do much. Okay. So I hope you are able to do this. Okay. Right. So people are moving out of YouTube meeting. It's all right. Did anybody get this running? This crop recommendation system. Did anybody get this running? Reach till the end? Yes, would be highly encouraging for me. Okay, meanwhile, while you are at it, running this crop type, let's quickly go back to our crop disease classification problem. Now we see the 20 epochs have run. Okay, so now we plot the validation and training loss graph. So you see here, originally the graph was plotted when there were 200 samples, because it was a large number of samples. So you see as the number of epochs progress, both training and validation accuracy decrease. Then a time comes when both the training and validation accuracy increase. Then a time comes when the training accuracy increases, more than the validation, or there's a drop in validation accuracy. That is where the overfitting happens. Though it is not clear when the overfitting is happening, but we can still say towards the end of 17th epoch or something, where if we look at this point, we see the training accuracy continues to increase, whereas the validation accuracy is somewhat going down. So maybe this is the point where to stop the training and take the snapshot of the model here. Okay, this was a graph that we got for 200 samples when we were on a larger data set. Let's plot the graph on the smaller data set. You see a smaller data set, number of boxes. The graph is somewhat, it's more zigzag. It's not falling into a particular pattern of how we see training and testing. It's primarily because the number of training samples is very less. Because to make the data set really small, so that it can be uploaded in a time-bound manner, and we can run the code. We took some shortcuts, and because of which this is sort of a messy graph. It does not ideally reflect how a machine learning training should proceed. So this we can still see that the training accuracy increases and the validation accuracy decreases. Okay, so once we have done that, then what do we do is, so yeah, so this is the graph. Yeah.
Sir, time is actually over, sir.
Okay, so I'll stop here. I'll stop here. So I've shared the code with all of you. And so, yeah, I've shared the code with all of you. So you can take a look and run. So, yes. So if you have any questions, I'll be happy to answer. At least one or two people have done the code, all three modules. Excellent. That is super, super encouraging for me, and shows that at least we are moving in the right direction. If you have any questions, I'll be happy to address. I hope this proved to be useful. This proved, or this will prove to be useful to you. Dr. Chaube and I were discussing that maybe some of the, like quite a few students take this and it helps them in their projects, research projects, and to explore other things. If you have any questions, I'll be happy to take.
So any question, please? Is there anyone who is curious to ask any questions? No question?
Okay. Thank you. I hope
Okay,
all of you.
okay, sir. Thank you so much, sir, for your practical session to detect plant disease, your extensive expertise in machine learning and its application in agriculture setting provided invaluable insights, greatly enhancing our understanding of how technology can transform crop management and disease protection. Your discussion on plant disease classification was particularly beneficial. You detailed various machine learning models that can accurately identify and classify plant diseases, offering practical strategy that can be implemented by agriculture professionals and researchers alike. This talk was not only informative but also immensely fruitful to everyone who involved, as it showcased real-world applications that optimize disease management in crops. Additionally, your hands-on session on soil moisture prediction using regression models was a highlight of the course. This segment effectively demonstrated how regression analysis could be used to predict soil conditions, which is critical for irrigation management and crop health. Your approachable teaching style made complex concepts accessible and engaging, allowing participants to see firsthand the practical benefits of integrating machine learning into agriculture practices. Overall, your contributions to the course were deeply valued. The knowledge and practical skills imparted during your sessions have equipped us with advanced tools to improve agriculture outcomes through technology. We appreciate your dedication to sharing your expertise and look forward to applying these insights in our ongoing and future projects. Thank you once again for a truly very valuable and inspiring educational experience. Thank you so much, sir.
Thank you, Chaube sir, for inviting me. And it was privilege to address the students. And I'd like to thank my PhD students, Anukul and Vikas, who made the data set on all the experiments possible at a relatively short notice so that all of us could benefit. Thank you. So I can leave, sir, now?
Okay.
Okay, thank you.
Thank you, sir. Participants, we may just, after lunch, we are going to start. As per schedule, the session is going to be started. Thank you, everyone. You may leave it.